When SpaceX launched Starship Flight 13, they intentionally compromised their own heat shield. If this thermal protection system fails, the rocket burns up. Achieving rapid reusability and fulfilling NASA's lunar landing contracts depends entirely on this shield surviving the trip back to Earth. The challenge is the material. To disperse the extreme heat of re-entry, engineers use extremely fine strands of glass and sapphire fibers. This creates a highly efficient thermal barrier, but the finished tiles are as brittle as a ceramic coffee cup. Intentionally stressing such a fragile system is a way to find its breaking point. By flying with simulated damage, engineers force weaknesses to surface in a controlled test, revealing how the structure behaves before carrying a human crew. The physics of the rocket itself create a constant mechanical strain on these tiles. Starship's stainless steel hull changes size during a mission, while the ceramic shield remains rigid. Loaded with cryogenic fuel before launch, the super-chilled metal hull shrinks, widening the gaps between the rigid ceramic tiles. During re-entry, friction heats and expands the steel. These gaps violently close, varying the spacing by 20%. This creates a physical bind. If the brittle tiles are placed flush against each other on the ground, they will crush each other during expansion. If they are spaced too far apart, superheated plasma will slip through and cut into the steel hull. Because a static shield cannot survive on a dynamic, breathing hull, engineers developed a flexible material to bridge the gap between tiles. Sealing these gaps has long challenged spacecraft design. The Space Shuttle used rigid gap fillers, but these added mechanical complexity and occasionally dislodged during flight. SpaceX's solution is a compressible material, layered like a crunch wrap, sandwiched directly between the tiles. This wrap acts as a dynamic seal. As the steel hull shifts between the deep cold of launch and the extreme heat of re-entry, the material compresses and expands to absorb the movement without transferring crushing forces to the brittle ceramic. Flight 13 was the first orbital opportunity to test if this dynamic seal could maintain its integrity under the actual pressures of a high-speed return. To measure the limits of this system, SpaceX painted specific tiles white to mimic the thermal environment of missing sections. This allowed them to monitor how the underlying steel and the new seals handled direct heat exposure. In earlier tests, they flew with tiles removed entirely over non-critical areas. They exposed the steel over the vacuum engine nozzles, using the inactive hardware as a safety buffer for the rest of the ship. For Flight 13, the diagnostic effort began before the ship even hit the atmosphere. Moments before descent, Starship deployed 20 Starlink V3 satellites. 6 of these satellites carried specialized camera packages. They were programmed to fly in formation above the ship, using laser links to beam high-definition footage of the heat shield back to Earth during the descent. Using a real-time diagnostic fleet provides a direct, high-resolution view of the entry environment that internal sensors alone cannot capture. Entering the atmosphere at 7 kilometers per second, Starship was enveloped in a pink and violet plasma sheath. The friction subjected the tiles and the white-painted test sections to thousands of degrees of heat. Unlike earlier flights, which often showed showers of sparks and debris during this phase, the plasma trail remained even. There were no visible indications of localized burn-throughs or trailing fragments. The ship successfully bled off its velocity, executed a bellyflop maneuver to arrest its descent, and relighted 3 Raptor engines for the final landing sequence. The new seals held, and the white test section survived. The ship protected its internal structure through the most intense portion of the flight. A moment of wonder. Starship performed a soft splashdown and remained structurally whole, floating intact in the Indian Ocean. Post-flight imagery showed the heat shield survived with minimal degradation. Even the white streaks from the simulated damage experiment were still visible after the plasma had cleared. This recovery suggests the thermal protection system can endure a full mission without requiring a months-long overhaul between flights. The data gathered from the satellite overwatch and the surviving tiles will be used to calibrate the next generation of shields. The goal is to refine these tolerances until the ship is ready to fly directly into the grasp of the launch tower's mechanical catching arms. By subjecting their hardware to a calculated trial by fire, SpaceX verified the durability required for a returning ship to survive its first tower catch.